Hello class, welcome to part 2 of our Unit 4 Skill 6 guided notes. This is the part where we will focus on the radicals that once we've simplified them require absolute value. So first thing you need to understand is that this little using of absolute value only applies when we're simplifying even roots. It will not apply to odd roots. So numbers 12 and 13 are not going to need to worry about absolute value. It's only something we worry about when we're simplifying even roots, and it has to do with the fact that we always want the positive root. Whenever we're simplifying an even root, we want the positive root. Back when we were learning about the square root function and graphing the square root function, what we called this was the principal root. We learned that when you see a symbol like the square root of 9, we only understand that to be positive 3, not plus or minus 3. Now, it's different than when we're solving equations, okay? So that's different than the scenario where you had x squared equaled 9, and then we had to square root both sides. That's a different scenario. In that scenario, we're solving for x, and this x value is being squared to equal 9. So the original x value could have been both a positive or a negative 3. That scenario is a little bit different than when you're just given the radical sign. If you're just given the radical sign like this and you're asked to evaluate the square root of 9, you are to understand that that symbol is only representing the principal root, the positive root. Even though we know that negative 3 times negative 3 is 9, when we see a symbol like this that does not have a plus or minus in front, we understand it to only equal the positive root, not the positive or negative root. So the function that we use to make sure that everything stays positive is absolute value, right? If you can remember the absolute value of a number, the absolute value of x is always greater than 0, right? The numbers that went inside could be negative, right? And you could plug a negative number inside, so x could be negative. But once you absolute valued it, the number that came out could only be positive. So negatives could go in, but only positives come out when you use the absolute value function, right? If you think about the graph of the absolute value function, it looked like this, where the x values were allowed to be negative or positive, right? Negative and positive x values were allowed, but when you look at the resulting y values, only positive y values were allowed, right? The graph only went up. It never went down. So the inputs, the numbers that went in, could be both negative or positive, but the outputs, the numbers that came out, only ever went up. They were only ever positive. So this function is perfect when I need to change something from being negative into being positive. That's what the absolute value does. And sometimes I'm going to need that when I'm working with variables and even roots. Okay, but first, actually, the first 5 examples, I'm going to show you cases that actually don't require the absolute value. And one instance is number 9, because there's a negative sign in front. So what that means is it wants only the negative root. And it's similar to the example I gave over here. When you see a radical sign with no sign in front, right, the default when there's no sign is positive. So this was saying only the positive root. Similarly, when you see a square root with a negative in front, it wants only the negative root. And the negative square root of 64 is negative 8. So we don't want absolute value here because we actually want the answer to be negative. So no absolute value needed on that one. Okay, number 10 is similar because you see it has the plus or minus sign in front. When you see a plus or minus sign in front of the radical sign, then it's basically telling us that they want both roots. Both roots are needed. So it's only when there's no sign written in front that we understand that to mean there's an implication that it means only the positive root. But if a negative sign is in front, then that means we want the negative root. And if a plus and minus sign is in front, that means we want both of the roots, the positive one and the negative one. So with 81, the square root of that is 9. And with n squared, right, the exponent equals the index. So that's an index size group. It's a perfect square. The square root of that would just be n. So this is plus or minus 9n. And I don't need absolute value here because I wanted both a positive and a negative answer. Now in number 11, there could be a need for absolute value because there's no sign in front. So that means the answer must be positive. And there's a variable involved, right? So when variables are involved and the answer must be positive, that's where we are on high alert. Maybe an absolute value is needed here. But let's take a look and see what happens when I try to break this down. So the first thing I need to remember is what it means to raise a binomial, right? X plus 1 is a binomial because it's two terms that need to stay together. When you raise a binomial to the fourth power, that basically means you are writing that binomial 4 times and multiplying it together. What that makes obvious to me is that I have 2 perfect squares. I have 2 index-sized groups, right? This is a square root, and I have 2 perfect pairs of x plus 1 and x plus 1. So I have 2 roots of x plus 1 and then x plus 1. 2 square roots. So when I take them out of the radical sign, it would be x plus 1 times x plus 1. This square root times that square root. Or I could write that as x plus 1 squared. So I know that this answer must be positive, but here's something else that I notice is it's being squared. Squaring something, by the way, is another way to keep it positive. So x plus 1 squared is already always positive. So I don't need to worry about using absolute value because this is already positive. I don't need to make something negative positive. So no absolute value needed here. I do want to pause for a moment though and just kind of consider what just happened because we could save time later by recognizing a little feature right here. So notice that I had x plus 1 to the power of 4, which meant I had 4 factors of x plus 1. And 4 factors of x plus 1 were able to split into 2 groups of 2. Basically what that is just division, right? I divided 4 into 2 groups of 2, and then each group of 2 was a perfect root. So I was able to take out 1 x plus 1 for every group of 2, which is why I had 2 factors of x plus 1 as my square root. In other words, what I can do is divide. When I'm taking roots, I can take the power that's under the root and divide it by the index to figure out the power that will remain when I finish taking the root, right? So this 2 was the power divided by the root. So that is something we can use moving forward to help us simplify these radicals. Once we get things written in terms of powers, we can take those powers and divide the roots to get the root, basically. So anyway, and then since the root here was an even power, that means it's already positive, therefore no absolute value is needed. Now 12 and 13 I already starred because those are odd roots, and odd roots only ever have 1 root. They already only have 1 root. In other words, these are already 1-to-1 functions. So we talked about that back when we were graphing the cube root function. We talked about how it was 1-to-1, and a cube root already has only 1 root. So the cube root of a positive number is going to be positive, whereas the cube root of a negative number is going to be negative, never both. Which makes it a lot easier to evaluate because we don't need to worry about the absolute value. You just don't need to worry about absolute values when you're dealing with odd roots. And in this case, we're looking for, since it's a cube root, we're looking for perfect trios. So if I factor 8, right, I get 2 times 2 times 2, and then n squared is n times n. So we can see we didn't have enough n's. I can't take out any n's because you need at least 3 to get a perfect third root. But I do have 1/3 root of 2. So I can take the 2 outside of the radical, and then I just leave the n squared underneath the cube root. That's my final answer, and no absolute value was needed because the answer could only ever be positive anyway, right? The cube root of 8 is going to be 2, not -2 anyway. So I don't need to worry about making it positive. And then in number 13, we have another odd root, and it's the odd root of a negative, but I don't need to worry about that because cube roots are allowed to be negative. So I just need to find the number that multiplies to itself 3 times to equal 125. So if we factor out 125, the number ends in a 5, which tells me it'll be divisible by 5. And let's see, that would go in 25 times, right? 5 times 25. And then 25 is another 5 and 5. Now, if I take into consideration the negative, then that would mean that just all of those 5s would have to be negative, because -5 times -5 would be positive 25. And then positive 25 times -5 is negative 125. What that tells me, or maybe I'll write it out, is that the cube root of negative 125 is just -5. And then 8 to the 9th, I'll write it out the long way this time, but for future, I need some more room here, so I'm going to write it down here. For future, I want to see if we can just divide, right, like we learned a second ago. But what I'll do is I'll rewrite 8 to the 9th as 8 to the 3rd times 8 to the 3rd times 8 to the 3rd. Because when you multiply bases, right, a times a, you add the powers, and 3 plus 3 plus 3 is 9. Or in other words, this is 9 factors of a, and 9 factors of a can be broken up into 3 groups of 3. 3 perfect trios. So this is an indexed size group. So is that, so is that, so is that. This is actually a perfect cube. Everything was a perfect index size group. So the answer will be 1 perfect third root of -5 and 3 perfect third roots of a, right? For each trio that acts as one root. So a times a times a, or -5a to the 3rd. -5a to the 3rd is my answer to this one. So if you look back here at the power, under the radical was a 9, and then the index was a 3. So if I divide 9 divided by 3, I get the same result, right? If I do 9 divided by 3, I get 3, which tells me that when I finish cube rooting this, my ending power for a will be 3. And again, no absolute value was needed here because it was a cube root, and cube root answers are allowed to be negative. So far we have seen 5 examples where no absolute value is needed. Okay, so there are many times where you don't need to worry about absolute value. But let's take a look at number 14. Number 14 is asking for a square root. Okay, there's no plus or minus in front, which means that the answer must be positive. And under the radical is a variable. And variables are things that vary, right? So x right now, the x that's inside, could be any real number. It could be anything. So x could be any real number at this point, okay, because it's being squared. So even if it were negative, that negative is being squared and disguising itself as a positive, which is allowing me to take the square root. But let's look at what we have here. We have x times x under the radical sign. So that's a perfect pair, right? This is a perfect square root of a square. We could divide, right? 2 divided by 2 is basically going to leave me with just 1x, right? The square root of x squared is equal to x to the first power, okay? But that's a problem because that x that we talked about could be any real number. It could be a negative number, and we're just letting that be the answer to this principal square root, which must be positive. this is the scenario where we come in and we say, okay, just to make sure, I'm going to put an absolute value around this x to make sure that the output is positive. See, the input, the x, right, could be any real number, could be negative. And that's the answer to this square root of x squared, which is supposed to be, must be a positive number. So by putting the absolute value around it, it allows for x to be negative, but for my answer to still be positive. So my final answer is the absolute value of x. And you might be thinking, well, how come when we were solving equations, we never said that, right? When we were solving equations like this, x squared equals 9, for example, right? We would tell you, okay, square root both sides. And then we would say, and then this becomes x, right? Square root cancels the square. That becomes x, and this is plus and minus 3. This is what we told you back when we were solving. Well, the truth is we were kind of skipping a step because really what we should have said is this. And it will still end up being the same, but really what happened was when you square root both sides, yes, the square and the square root cancel each other out. That is true. But it leaves you with the absolute value of x. Technically, the square root of x squared is the absolute value of x, and that equals 3, because the square root of 9 is the principal root, which equals 3. And then from there, we solve an absolute value equation. And if you remember, solving an absolute value equation, you're supposed to make two different equations. One where the inside equals the positive value, and then the other one where the inside equals the negative value. So that's how we end up with this as our answer, plus and minus 3, was technically because when you square root x squared, you get the absolute value of x. Let me show you, if you don't believe me, let me just show you really quick on Desmos. So here on Desmos, you can see I've got this equation, y equals x squared, the square root of x squared, I mean. But if you look over here at the graph, it is not showing just the line y equals x, right? If I type in y equals x, that is a line that has a constant slope of positive 1, right? Y equals x is different than y equals absolute value x. Y equals absolute value x looks like this. If I take the blue one off, right? Y equals absolute value x is the same graph as y equals the square root of x squared. Those are the same graphs because they are the same value. Both of them, in both scenarios, the x is allowed to be negative, okay? In both scenarios, the x is allowed to be negative, right? Notice I have all these negative x's, and those negative x's have points on this graph. But the y value does not have any negative values. Look, there's missing negatives down here. So y equaling the square root of x squared will produce the same outputs as y equals absolute value of x will produce. It's just a fact. It's just the truth. We just haven't told you that truth until now because now we feel like you're ready for it. So moving forward, we want you to understand that when you have to square root something that could potentially be negative, or you have to square root something that is currently positive, but once you square root it could be negative, we have to put absolute value around it to obey the rules of the principal root. And even Desmos knows that as well. So moving on to number 15, it's a similar case, right? I've got an even root, okay? Which means, and there's no plus or minus sign, which means that the answer must be positive, okay? And so I need to be careful when I get to my final answer to recognize if it needs absolute value. And like number 14, this m, right, the m could be any real number because it's a variable. So it could be any real number. It's allowed to vary, and it's being raised to an even power. So m could be any real number, and m to the fourth would still be positive. That's the real thing, is that m by itself could be any real number, but then when you raise it to the fourth power, it's positive, which is allowing me to put it under an even root, right? I can take the fourth root of a positive. Then when I go to simplify this, I notice I have a perfect quartet, right? It's a perfect grouping of 4. It's an index size group. So that's one perfect fourth root. Or I could divide, right? 4 divided by 4 is equal to 1. Power divided by index is equal to 1. So the answer to this would be m to the first power. But we just said a moment ago that that m could be any real number, but the answers to this must be positive. So I need to put absolute value around it to make sure that the output stays positive. So again, let's check this on Desmos to show you that it really is true. So now, let me X these out. So we're going to do y is equal to the fourth root of x to the fourth power. And lo and behold, right, I get the same thing again. I get y equals the absolute value of x. It's the same thing, right? Those functions are one and the same. And it's the same, and it's for the same reason. Because the inputs of x are allowed to be negative or positive, but the outputs, what comes out along the y-axis, must only be positive. So let's recap the rules. Let's go down here. This is in general, this is what you need to remember. Okay, you need to remember even, odd. This is the only time when you will be required to use absolute value. So what do those words mean? Well, it means that you're starting with an even index. So automatically I can rule out 17 is not going to need absolute value because it does not begin with an even index. It begins with an odd index, which is another reason why I love odd roots. Okay. Then you look to see if the exponents underneath the radicand, underneath the radical or in the radicand are even. So right now I'm noticing 16 is probably going to need absolute value because I've got an even index and I have even exponents underneath the radical or in the radicand, inside basically. Even index, even powers. And then when you simplify, if the power comes out to be an odd in the end on the answer, that's when you'll need absolute value. So let's look at 14. 14 had an even index of 2, an even power of 2 under the radical, and then when I simplified, there was a power of 1, which is technically odd. That is why I needed absolute value. 15, same scenario. I started with an even index, and I had an even power under the radical, and then when I simplified, right, when I divided power by index, I got an odd number, 1. And that was why I needed the absolute value. And that is because negative numbers, when they're raised to an even power, become positive. And so that's what allows me to take the even root of those numbers because I'm taking the even root of a positive value. But when you take the root and it brings it back to the odd power, that suddenly has the potential of being negative again, and therefore I need to slap an absolute value around it to keep it positive. Notice in 13 and 12, I didn't need absolute value at all because the index was odd. So right away, I didn't even need to worry about it. And in 11, I didn't need to worry about it because even though I had an even index and an even power, when I simplified and divided power by index, I ended up with an even power. So I did not need absolute value because when you raise a variable to an even power, it already is staying positive. So it's only when you have an even index, even exponents underneath the radical, and then an odd exponent on your final answer. That is the only scenario where you will need absolute value. Let's try a few more and see if we need it. So 16, we're definitely going to need it because I have even index, even powers, and I can see one of those powers is going to reduce to be an odd. So I'm going to do this the long way and then I will show you the short way. But I can say that a to the fourth is already an indexed sized group, okay? N to the 8th I could write as n to the 4th times n to the 4th because when you multiply same bases, you add the powers, and 4 plus 4 adds to 8. So I can see everything is actually a perfect fourth root, right? I have 3 index-sized groups. They all match the index. So these are all perfect fourth roots. A fourth root of A, another fourth root of N, and then another fourth root of N. So I can simplify this and say this is A times N, which is AN squared. Short way would say just divide the powers, right? Divide. Or divide the power by the index. 4 divided by 4 is 1, and 8 divided by 4 is 2, right? That's 4 divided by 4, and that was 8 divided by 4. So that's the short way, just divide the powers. Now this one ended up being odd, right? A to the first ended up being odd, so that's the one that needs absolute value. Because it began with an even index, it continued with an even power under the radical, and then it finished or finalized with an odd. It went from even to odd. So that's the one that will need an absolute value. So the final answer for this would be the absolute value of A times N squared. That's our final answer. We only put absolute value around the one that needs it, okay? Then we look at 17 and we go, we take a nice breath, sigh of relief, because that's an odd power. I don't need absolute value when the power begins. Sorry, it's an odd index, index. When the index is odd, no absolute value is needed. So I'm just going to go ahead and simplify the root. I'll go ahead and break down 32. So 32, we factored this one in the previous video, is basically composed of 5 factors of 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So it's a perfect fifth power. So then we have a fifth root of 2, and then x to the fifth is a perfect fifth, perfect power of 5, and then I'm going to break y to the 10th into 2 groups, right? So what I see is that I have 4 indexed sized groups, because my index is 5. There's 2 to the 5th, x to the 5th, y to the 5th twice. So for each perfect 5, that's one perfect fifth root. So a fifth root of 2, a fifth root of x, a fifth root of y, and then a second fifth root of y. So my answer to this would be 2x times y, which is 2xy squared, and no absolute value needed. And as a reminder, you can do 5 divided by 5 to get x to the first, 10 divided by 5 to get y squared. Now with 18, you might say, oh, we don't need the absolute value because there's a negative sign in front. Well, actually, we kind of still might, because now they're saying that they only want a negative answer. When you see a negative in front, that means the answer must be negative. I can't allow it to turn positive. So I'll show you how that works. So this one actually may end up requiring absolute value as well, so that I can keep the answer negative. So first I'll start by just looking at the 121, right? That breaks into 11 and 11. A to the 6th, I could break into 3 perfect A squareds, and then I already have a perfect B squared. So I find that I actually have 1, 2, 3, 4, 5 indexed sized groups. For each index sized group, that's a perfect square root. So I have a square root of 11, a square root of A, square root of A, square root of A, and a square root of B. And all of those things are being multiplied together. So this is equal to negative, because that was already in front, 11 times A times A times A times B, which is negative 11 A to the third B. And again, you can divide, right? 6 divided by 2 would give us the 3, and then 2 divided by 2 would give us the 1. So if, and remember, A and B could technically be negative, could be any real number. So once you square root A to the 6th and B squared and just get A cubed and B, they could technically be negative, and if they were negative and they multiplied to negative 11, that would turn this whole value into a positive. So oddly enough, we're going to put absolute value around a cubed b to keep this part positive. If I keep that part positive, then it will keep the entire answer negative. So we keep this part positive to keep the entire answer negative. So you've seen how this works, and I know it probably seems so tedious, just like such a small detail, but it's really good to try to wrap your brain around when we would need the absolute value, when we wouldn't, because it really forces us to think about domain and range, input and output. So I want you to try 1 and 2, pause your video here and come back and check your answer. Welcome back. So for the first you try, you might notice that the index was odd, which means this problem does not require absolute value. So you just solve it like a normal simplifying radical. Split up the 40 into 2, 2, 2, and 5. So I had 3 2s and a 5. Break up not really a to the third, but break up y to the 5th into y to the 3rd and y squared, because 3 plus 2 adds to 5. And then we see we have 3 perfect cube roots of 2a and y, so we can bring those out. And then we had a 5 and a y squared remaining under the cube root. So we multiply all of that together. Then for the second you try, we noticed that the index was even, which meant we might need absolute value. The powers inside continued to be even, again indicating we might need absolute value, right? Because the trend is even, even, odd. And then for the x, the ending power after I simplified was odd. And so that particular variable needed absolute value around it because it followed the even, even, odd trend. And then I went ahead and broke them all into groups of 6, but we could have divided here because it divided evenly. 18 divided by 6 is 3, 12 divided by 6 is 2. And then just recognize x ended with an odd power and put absolute value around it. So that is our lesson for today. There's a worksheet that goes with it. I really want you to practice and check your answers. And good luck on your quiz on Friday. Bye-bye.